Hey everyone, welcome back to the channel. Today we're going to talk about the AWS Certified Generative AI Developer Professional Exam, or AIP-C01 for short. If you've been wondering what this exam really involves, how long it takes, and what kind of questions you'll face, stick around. We're going to break it down together. First up, the exam duration. The AIP-C01 beta exam is 205 minutes long. Yep, that's just over 3 hours to tackle all the questions, so pacing yourself is key. For non-native English speakers, there's a 30-minute accommodation available, which can really help if you need a little extra time to read and process the questions carefully. Now let's look at the number of questions. The beta version has 85 questions total. These include a mix of scored and unscored questions. Think of unscored questions as the exam's way of testing out new material for future versions. You won't know which ones are unscored, so it's best to give every question your full attention. In a standard professional exam, you'd typically see about 75 scored and 10 unscored questions. But for the beta, the total comes out to 85. All right, let's talk question format. You'll encounter multiple choice questions, which have one correct answer, and multiple response questions, where you have to select 2 or more correct answers from a list of options. The exam guide also mentions possible ordering and matching questions, although they may not appear in every exam version. So it's good to be ready for different formats and think critically about each question. Testing options are flexible too. You can take the exam at a Pearson VUE testing center if you prefer a traditional in-person environment, or you can opt for an online proctored exam from the comfort of your home. This flexibility allows you to choose the testing style that makes you most comfortable. Finally, let's talk about scoring. The AIP-C01 is a pass-fail exam. Your performance is reported as a scaled score ranging from 100 to 1000. The minimum passing score is 750. Keep in mind that this is a scaled score, which helps equate results across different versions of the exam to account for slight differences in difficulty. So, what does this really mean for you as a candidate? You've got over 3 hours to carefully navigate 85 questions that test not only your technical knowledge, but also your practical ability to integrate foundation models into real-world applications. You'll need to be comfortable with multiple choice and multiple response formats, understand how to manage your time effectively, and be ready to tackle some unscored experimental questions that could appear anywhere in the exam. All right, friends, that covers the core logistics of the AWS Certified Generative AI Developer Professional Exam. Remember, the key is preparation, understanding the question types, and knowing how the scoring works so you can pace yourself and maximize your chances of success. So, all right, now let's look at today's practice exam question 1. Which memory strategy captures explicit user preferences and context for personalized AI interactions? Imagine you're chatting with an AI assistant every single day. You tell it once that you hate cilantro, you love dark mode, you prefer for short answers in the morning because you're half asleep, and you always want travel plans with window seats. A good agent should just remember that stuff, right? Forever, not make you repeat yourself like a bad waiter. So here's the multiple choice lineup we're looking at. Semantic memory, that's general facts and world knowledge. User preference memory, Memorgy inside Amazon Bedrock Agent Core. Summary memory, the running narrative of what just happened. Raw chat logs, just dumping everything into a giant text file. The correct answer is option 2, user preference memory strategy in Agent Core. Let's look into why. It captures explicit and implicit user preferences. Explicit preferences are directly provided by users, like favorite topics, settings, or choices. Implicit preferences are inferred from user behavior, such as frequent commands, click patterns, or interaction style. Together, they allow the AI agent to understand what a user wants without needing repeated instructions. Maintains context across multiple sessions. The memory strategy ensures that user context is preserved even when a session ends. For example, if a user asks for specific filters or settings today, the agent remembers them next time. This continuity enables a personalized and seamless experience. Continuously updates and consolidates preferences. As users interact over time, the system reconciles new information with existing preferences. Conflicts or redundancies are intelligently merged so that outdated or irrelevant preferences are removed. This keeps the AI's understanding accurate and adaptive. Enhances decision-making for the AI agent. By knowing user preferences, the agent can prioritize responses, recommend relevant actions, and avoid unnecessary repetition. It helps the AI choose between multiple options based on what the user values most. Supports personalized, user-centric interactions. AI can tailor responses, suggestions, and workflows to align with individual user needs. This increases engagement, satisfaction, and trust in the AI assistant. For example, in a GenAI application, it ensures outputs are contextually relevant and user-aligned. Super useful for knowing that Paris is the capital of France, but it has zero clue that you specifically want your email summarized in some bullet points. Summary memory, great for remembering, oh yeah, yesterday we were planning a trip to Japan, but it doesn't extract the fact that you always fly business class or that you're vegetarian. Raw chat logs, yeah, technically all your preferences are buried in there somewhere in a 400-page transcript. Good luck finding them quickly when the model has 8 seconds to respond. And then, boom, we land on the winner. User preference memory strategy. Let's zoom into the diagram together. You can see explicit preferences coming in on the left, stuff the user directly says, I like concise answers, call me Alex, never suggest horror movies. Those go straight into the user preference memory cloud. On the right, implicit preferences and contextual signals flow in too. Maybe the agent notices you always pick the cheapest flight, or you only chat after 8 p.m., or you thumbs up every response that uses emojis. All of that gets intelligently parsed and stored. Hang on, because this part's super important. There's this box in the middle called preference consolidation. This is the magic sauce. Every time a new preference comes in, the system doesn't just dump it on the pile. It checks. Do we already have something about response length? Okay, the user just said they want even shorter answers in the morning. Let's update that rule and merge the two. No duplicates, no contradictions, just a single source of truth that keeps getting smarter. So, what does this really mean for you? It means the next time you open the app, even if it's been 2 weeks, the AI instantly knows you're Alex, you hate cilantro, you want dark mode, short answers before coffee, and window seats. No awkward, wait, who are you again moment. It feels like a friend, not a robot that got amnesia. You might be wondering, okay, but can I just do this myself with prompt engineering? Sure, for about 5 minutes. As soon as the conversation gets long, the prompt hits the token limit and your carefully crafted preference list gets chopped off. User preference memory lives outside the context window, so it's always there, always up to date, no matter how long the chat goes. Bottom line, if you're building agents that need to feel personal, shopping assistants, productivity buddies, health coaches, whatever, this dedicated preference memory layer is rapidly becoming table stakes. All right, let's look into the next question. If you're building anything with RAG, Retrieval Augmented Generation, or you just love making your AI actually know what it's talking about, we're answering one of those questions that pops up in literally every GenAI interview or system design meeting. How do you actually know if your knowledge base retrieval is any good? So here's the exact question that was asked. A GenAI platform wants to assess the retrieval quality of an FM augmented knowledge base. Which approach is most effective? And then we get 4 options. Option 1, track only the number of model invocations per hour. Option 2, use relevance scoring, context matching, verification, and retrieval latency. Option 3, monitor memory usage without analyzing retrieval performance. Option 4, count total token usage for queries. All right, pause the video for 2 seconds if you want to guess. I'll wait. Done? Cool, let's jump in. Now, this one's really interesting because on the surface, all of these sound kind of technical and reasonable, right? Like, oh yeah, we should track how many times the model gets called or how many tokens we're burning. That must be good monitoring. But here's the thing. None of those actually tell you if the stuff you're pulling out of your knowledge base is useful or correct. It's like measuring how many times you open the fridge without ever checking if the milk is spoiled. You can open it 1 million times an hour, still doesn't help if everything inside is garbage. So let's look at the diagram together, because this flowchart makes everything crystal clear. Imagine the user types a prompt, something like, "What's our return policy for enterprise customers in Europe?" That prompt shoots over to our retrieval system, and boom, we go grab chunks from the knowledge base. Up until this point, everything looks normal, but now comes the part most teams completely skip. First, we run relevance scoring. Think of this as asking, on a scale from 0 to 1, how much does this document actually answer the question? Not just keyword matching, we're talking semantic relevance. Did we pull the 2024 Enterprise Return Policy PDF, or did we accidentally grab the 2019 blog post about t-shirts? Huge difference. Next step, context matching verification. This is the, wait a second, does this chunk even make sense when we shove it into the prompt? Because sometimes you retrieve something super relevant in isolation, but the second you paste it next to the user's question, it contradicts the instructions or creates confusion. This check is what keeps your model from hallucinating or confidently giving wrong answers. And finally, retrieval latency measurement. Look, nobody wants to wait 4 seconds every time they ask a simple question. If relevance is perfect, but it takes 1200 milliseconds to get the docs, users are going to bounce. Speed matters just as much as correctness in production. When you put these three together, relevance scoring, context verification, and latency, you finally have a complete picture of retrieval health. You can see exactly where things are breaking. Are you getting irrelevant docs? Are they relevant but clashing with the prompt? Or is everything perfect but just slow? That's why the right answer, hands down, is option 2. The other options? They're what I call vanity infrastructure metrics. Model invocations, memory usage, token counts. They tell your ops team the system is alive, but they don't tell your product team the system is useful. I've seen teams proudly show graphs of 99.9% uptime and 2 million queries per day, and then you test it and the answers are wrong half the time. Metrics without meaning. So what does this really mean for you? If you're building or evaluating a RAG system right now, start instrumenting these 3 signals today. Add a little relevance scorer. You can even use a tiny open source model for this. Log your latency from query to retrieve chunks, and add a quick context match check before you send anything to the big foundation model. You'll catch 90% of the garbage before it ever reaches your users. All right, quick recap because I don't want you to forget this. Best way to measure retrieval quality: relevance scoring plus context matching verification plus retrieval latency. Everything else is just noise dressed up as monitoring. So the correct answer is option 2. Use relevance scoring, context matching verification, and retrieval latency measurements. Retrieval quality directly influences FM response accuracy, making evaluation essential for reliable RAG systems. Relevance scoring verifies whether retrieved documents meaningfully match user intent, improving context integrity. Context matching verification ensures retrieved items align with the model prompt and avoid hallucination-prone mismatches. Retrieval latency measurement confirms the system returns relevant documents quickly, maintaining usability and responsiveness. Combining relevance, context alignment, and latency provides a complete retrieval quality assessment, enabling targeted optimization of the knowledge base and retrieval pipeline. All right, let's look into the next question. So here's the scenario. A GenAI team is trying to figure out the smartest, safest, and most bulletproof way to decide which model actually goes live for their customer support chatbot. They've got 4 options on the table, and only one of them is truly robust. Let's read them together real quick. Option 1, log all responses without performing systematic scoring. Option 2, track only average response length without assessing correctness. Option 3, monitor only server CPU usage during inference. Option 4, multi-model evaluation, A/B testing, canary deployment, and cost performance analysis, including latency to quality ratios. Okay, pause for a second. If you had to pick one right now, which one feels like the grown-up, enterprise-grade answer? Yeah, I thought so too. But let's walk through why the first 3 are honestly kind of scary if you care about happy customers. Starting with option 1. Just logging everything and calling it a day. Look, Logging is great, we all do it, but if you're not scoring relevance, correctness, tone, safety, you're basically hoarding data without any insight. It's like recording every phone call in a call center and never listening to a single one. You've got terabytes of we answered something, but zero clue if it actually helped the customer. Feels like a trap, right? Option 2, only watching average response length. Bro, come on. I've seen models that write beautiful 500-word essays that are completely wrong, and I've seen models that say, here's your refund code, XYZ123 in 6 words and solve the problem instantly. Length tells you literally nothing about quality. It's like judging a pizza by how big the box is. Option 3, only staring at CPU usage. Okay, I get it. Costs matter. Nobody wants to burn cash on GPUs. But imagine your doctor only checked if the MRI machine was using too much electricity and never looked at the actual scan. That's what this feels like. You can have the cheapest, coolest running model on the planet and still make customers furious because it hallucinates refund policies. Now, let's talk about option 4, because this is where things get exciting. This is the full professional playbook, the one that big teams actually use when millions of customer conversations are on the line. First, multi-model evaluation. You're not just trusting one benchmark leaderboard from 3 months ago. You're taking GPT-4o, Claude, Llama 3.1, Gemini, whatever. You throw them all at your real customer support tickets. Score them on relevance, empathy, factual accuracy, policy compliance, everything that actually matters to your business. Suddenly you know who the real champion is instead of hoping the blog post was right. Then A/B testing. You split real traffic, maybe 50-50, and you watch metrics that actually move the needle. Resolution rate, customer satisfaction score, escalation rate, average handling time. Not vibes, not guesses, hard data from real humans. Next, canary deployment. This one's my favorite. You don't yeet the new model to 100% of your users and pray. You start with 1%, maybe 5%. You watch like a hawk. If CSAT drops, if escalations spike, if people start tweeting, why is the bot drunk today? You roll back in seconds. 0 customers permanently harmed. It's like having an undo button for production. And finally, cost performance analysis, the grown-up conversation. You plot latency on one axis, quality on the other, and you ask the million-dollar question, where's the knee in the curve? Because going from 92 to 98 on quality might cost you 4 times the money and add 800 milliseconds of latency. Is that worth it? Sometimes yes, sometimes no, but now you're making decisions with data instead of feelings. So yeah, option 4 isn't just the correct answer. It's the difference between shipping something that works and shipping something that scales safely while keeping both your customers and your CFO happy. If you only take one thing away from today, let it be this. Never pick a model based on a single shiny metric. Build the full loop, evaluate rigorously, test with real users, roll out carefully, and always know the dollars and cents trade-off. All right, that's it from me. So, correct answer is option 4. Multi-model evaluation, A/B testing, canary deployment, and cost performance analysis, including latency to quality ratios. Choosing the best FM configuration for a customer support chatbot requires evaluating output relevance, correctness, and fluency. Multi-model evaluation identifies the strongest candidate among multiple foundation models or configurations. A/B testing compares different models or settings in controlled environments, revealing real-world performance differences. Canary deployment safely exposes a new model to a small portion of traffic, minimizing risk during rollout. Cost performance analysis, especially balancing latency with quality, ensures the model is both efficient and effective in production.